chapter
Okay.
10. This is interaction between particles. That's what we're going to start with. Okay. And it's going to go through solids, liquids, and gases. Solids are tightly bound. They form their own shape. Liquids are looser bound. They take the shape of a container. And gases are very loosely bound. Okay, so the tightest bound is going to be the solid, where the different forces. Now we're going to talk about two types of forces. We're going to talk about intermolecular and intramolecular. Intermolecular is within the molecule. Intramolecular is between molecules. So in other words, we take water for an example. We know we got H2O. This is an intermolecular force inside the molecule. Water is bounded. It's a polar bond. Remember, this is delta minus because oxygen is more electronegative than hydrogen. This is delta plus. This is delta minus. This is delta plus. And opposite charges attract. So there's a force between the water molecule. This is intramolecular. That's what we're talking about with the different forces. Inter is between the inside the molecule. Intra is between molecules. Those are different forces. Okay. Solids are more tightly packed than gas, than liquids. Liquids are more tightly packed than gases. Okay. So these intramolecular forces are what gives compounds their physical properties, how hard they're bound together, like melting points and boiling points. The harder they're held together, the higher the boiling point, the more energy it takes to break that bond between molecules. So the tighter they are together. In one of the book's examples, it says you have methane with the CH4, you have ammonia, which is NH3, and you have water, which is H2O. Okay. If you look at the boiling point, the highest boiling point is going, of those three, is going to be water. That's the highest intramolecular forces. This is hydrogen bonding, which you're going to talk about, which is a very strong bond. Okay. We'll talk about that in this chapter. And then you look at methane gas, which is CH4, again, carbon, hydrogen. Okay, it is a non-polar molecule. All the forces cancel out. So there is no attractive forces between molecules. It's very slight. Okay, so this would have the lowest boiling point. This would have the highest boiling point. And that's all due to these intramolecular forces, the forces holding the molecules together. Okay. Make sense so far? Okay. So now we got solids and liquids in the second part of the chapter. And we're looking at melting points for ionic compounds. Ionic compounds are going to have very high melting points. Okay. Because they have charges holding together, like sodium chloride, Na plus, Cl minus. Okay, they got those actual charges holding together, so they're going to be very hard to break apart and hard to melt. Okay. Again, melting point like sodium chloride is 801 degrees centigrade. A lot more than water. Because an ionic bond is an extremely strong bond for an intermolecular force. Okay? And the more charges you have, the stronger the bond. So if I gave you a list of NaCl, let's see what else I can put in here. Potassium, bromide, magnesium, chloride, and let's put another one in here of barium iodide, and let's see what else I want to make sure I'm right. Calcium oxide. Which one of those would you look at have the highest melting point? Okay. You look at Na plus, that's a plus and a minus. This is a plus and a minus. This is 2 plus. and a minus. This is 2 plus and a minus. This is 2 plus and 2 minus. The 2 plus and 2 minus, remember calcium has a +2 charge, oxygen has a -2 charge. Okay? That's going to hold it tighter than just a plus and a minus, or a 2 plus and then a 1 minus. So the hardest bond to pull apart, the highest melting point in this list would be calcium oxide. Okay? Because the charges holding it together make up that greater intramolecular force, where you have double the charges rather than sodium chloride, which is just single. Okay? So it's very hard to melt those substances. Okay? You also have what's called dipole-dipole interactions. A dipole is a polar bond. We took a polar bond like hydrogen chloride. Remember that has polar, but chlorine is much more electronegative. Chlorine is like a 3.0, hydrogen is like a 2.2. If the number, so this is delta minus, this is delta plus. So we can line up with other ones. The plus is going to attract the minus, H plus, Cl minus. H plus, Cl minus. The delta plus, delta minuses. Okay. So you're going to have these charges, this bond between the plus and the negative of the molecule. And this is called a dipole, from a polar bond. Okay. Those are dipole-dipole forces. Okay. And we have special forces that are dipole called hydrogen bond. Let's go into let's get into hydrogen bonding on that. That's next up. So you got ionic forces, which are extremely hard holding together. And you got these dipole-dipole forces, which are kind of weaker forces because there's just a small charge on that. Okay. And then also what's called hydrogen bonding. Hydrogen bonding is between the two. Hydrogen bonding is a very special type of dipole forces. Hydrogen bonding occurs when hydrogen is bonded to a small, highly electronegative element like nitrogen, oxygen, or fluorine. So when hydrogen is bonded to one of those, you will get hydrogen bonding. Okay. So in other words, hydrogen bonding, we had water. Let's do ammonia, for example. Nitrogen. This is the Lewis structure for nitrogen. Okay. So the high electronegative element attracts the electrons in the bond. So these are all delta minus charges out here. And this is a delta plus. Okay. So when this central atom is a nitrogen, an oxygen, or a fluorine, we're going to have hydrogen bonding because the electron is going to be pulled so far towards this inner element that you're going to get a net small charge on the outside. And then this will bond to another nitrogen because the nitrogen is positive. Did I do that right? I did that backwards. I'm sorry. The nitrogen is negative. I drew my charges wrong. H's are positive. Okay. So nitrogen here is negative. These electrons here. And the H's are positive. Sorry. Delta plus, delta plus. Okay, because the electrons are drawn towards the nitrogen or the oxygen or fluorine because they're highly electronegative. And they're going to draw towards that, giving it a slightly negative charge, leaving the hydrogen with a positive charge. So that's why ammonia will dissolve in water, like Windex. Okay, is ammonia in water because ammonia, like I said, delta minus, hydrogen, 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 delta plus. Now water molecule is going to be delta minus and delta plus on the oxygen. So the minus and the plus bond to each other. And the same thing here, another oxygen for water, and the minus and the positive form a bond. And this forms a whole network here. And it dissolves in water due to the hydrogen bonding, the opposite charges attracting. And this forms a higher melting point than would be expected because that intramolecular force is greater. That's why things dissolve and other things. Like dissolves like is a rule. Polar things dissolve in polar because of the hydrogen bonding. Okay. So if you want to compare the properties, let's see, they're comparing methane, hydrogen cyanide, and water. So let's compare those. It's got methane, which you said is CH4, hydrogen cyanide, which we drew the Lewis structure for these before, and water. Hydrogen. So look at these three compounds here. Which one would have the highest boiling point, highest melting point? Okay. You should be able to tell by now which has the lowest melting point, which has the highest melting point or boiling point. Okay. If you look at methane, right here, there is no polar bonding. This is what's called dipole. This is what's called an induced dipole. Okay. It means there's some bonding because, remember, electrons are spinning around all the time. And at any given time, there's going to be more on one side than the other. And that will cause a slight dipole. So these hydrocarbons will hold each other together and tend to grip together due to this induced dipole that they have. That's why gasoline's a liquid. It's octane gas. It's a hydrocarbon. Hydrogen cyanide actually has a delta minus and delta plus, has a polar bond. So it's going to have dipole-dipole bonding. They're going to have two dipoles are going to be attached to each other. And water has hydrogen bonding, which has a hydrogen bonded to an oxygen, a nitrogen, or fluorine. So hydrogen bonding is going to exhibit the highest boiling point. Okay? And the second would be the dipole, with hydrogen cyanide has a polar bond. And the last would be the induced dipole. So an induced dipole is basically carbon. Let's bond these together. Okay, these electrons are going around. At any point in time, some of the electrons are going to be more towards carbon than hydrogen just by sheer coincidence, right? Because electrons are going around the atom. Okay. That's going to induce a slight, very small negative charge, very small positive charge. Okay. That's going to cause the electrons to pull towards them on the next one. So that's going to cause the electrons here to pull this way, making this a small minus, and this a small plus. Okay. This is a very weak bond. That's why gasoline, which is as a hydrocarbon, evaporates so quickly. It's a very weak bond. It's just by happenstance, just by coincidence, more electrons are on one side than the other. And that creates a temporary dipole. Okay? And that affects the one next to it, which affects the one next to it, which affects the one next to that. Because it causes the electrons to shift towards that charge. Because the electrons are a negative charge. And if there's a positive charge induced somewhere, the negative charge is going to incorporate, or going to be drawn to it. And that makes a weak bond. So this has the lowest, or this has the lowest melting point. And methane has a boiling point or melting point. This has minus 162 degrees centigrade for its melting point. Okay. Hydrogen cyanide has a polar bond. It's going to track a little bit stronger. Okay. That has 26 degrees centigrade for its boiling point. And water is 100 degrees centigrade. It has hydrogen bonding. Hydrogen bonding is very strong. That's why there's a surface tension with water. You ever wax your car, then pour water on it? What happens to the water? It rains. The water beads up, right? Because water has bonding which holds it together. So instead of just sliding it off the car, it groups together into a bubble. Okay? That's called your surface tension. You ever skip a rock across water? Okay? The only reason you can do that is because of surface tension. If you fill a lake with gasoline, okay, gasoline has no surface tension. You try to skip a rock, it's going to sink every time. Because there's nothing for it to bounce that rock off. There's nothing holding the forces on the top of that water together. You ever watch those little bugs crawl across water? That's because it has surface tension. And they're able to do that because of hydrogen bonding. Okay, it tends to hold things together into a network. Okay, these induced dipoles are referred to in the book. They're also called London dispersion forces. You'll see that a lot in biology. You have London dispersion forces. This is a very weak bond. And these are the induced dipole, okay? Because of how the electrons are randomly on one side or another, and they create a temporary charge. Because there's more electrons on one side or more electrons towards one of the sides of the bond than the other side. And that creates a small charge. Okay. So you have to worry about polar bonds, non-polar bonds, and hydrogen bonding. Remember, hydrogen bonding only occurs with hydrogen. And only when hydrogen is bonded to nitrogen, oxygen, or fluorine. In any of those three cases, you will have hydrogen bonding. Let's give another example from the book here. Let's say, it says classify the following ionic, metallic, or covalent solids. Okay, let's give you an example. You can follow from the book here. So they give you three examples. They give you potassium nitrate, and they spell them out. So let's put potassium nitrate. Let's put phosphorus tribromide. And they give you chromium. Okay, and they want to know whether the bonds that hold them together are ionic, metallic, or covalent. Okay. This compound here, potassium nitrate, is it ionic, covalent, or metallic? Which one would it be? Any takers? So it'll be either ionic, covalent, or metallic. Can everybody hear me?
Yeah, we can hear you.
What's
I
that?
hear you. I just don't know.
Just don't know.
Okay.
Is it ionic?
Perfect. It's ionic. Potassium is plus, NO3 is a polyatomic ion negative. That creates an ionic bond, positive, negative charges. So this would be ionic. Okay. Potassium bromide. Those are two nonmetals, right? Two nonmetals are what? We said two nonmetals are covalent. And chromium is an element. And it's a metal. It's a transitional metal. So that's the metallic bonds that hold them together. Okay? So you got your ionic bond, a covalent bond, or your metallic bond. Okay? Looking at these compounds, let's do the next one here. Let's take ethene, carbon. Let's look at the Lewis structures. Okay? Or we have urea. Looking at these two structures, number one, number two, if that was on the test, on your final, which one would you say had the highest melting point? Which one's going to be held together tighter? One or two?
Would it be two?
It'd be two. Perfect. Exactly. It would have to be because two has a polar bond here. This is delta plus. This is delta minus because oxygen is more electronegative. Whoops. I went backwards here. Oxygen is more electronegative. I can find my picture again. Than carbon. So now you got a polar bond. You have a dipole. It's going to bond to the next one and hold together tighter. Whereas this one is going to be London dispersion forces. This one's going to be dipole-dipole interaction. That's how you look at these. You look at their structure, you look at their shape, you look at the charges on it, what it's going to do with the polarity of the bond, and you say which is going to be held together tighter between the molecules. The one that's held together tighter between the molecules is going to have the higher melting points. Okay. We talked about dispersion forces. We talked about that. Perfect. Different polymers. Polymers are just units. A polymer is a manufactured unit that is just repeating units that are bond together. Usually done by double bonds or by a fluorocarbon. Let's say we have carbon, carbon. Let's see, we have CH, Cl, CH, CH. And this is a repeating unit. In other words, this is bonded to another CH, Cl. This is bonded to another CH, Cl. And so on. This repeats over and over again on both sides. Again, CH, ClCH. And these units just repeat. That's a polymer, like Teflon, non-stick coating surfaces on your pants, things like that. These are polymers. These are produced chemically. They take one unit and they link it to the next one. And they link these units over and over. It's represented by an N here, which just means multiple units of that repeating over and over and over again. And this is what's called a polymer. And they have certain properties as these extend out. Any questions so far on that? We'll get into gases. Okay. Gases have special properties. We have all kinds of rules and laws and formulas for gases. Okay. We define gas by pressure, volume, and temperature. Those determine the forces of a gas. Okay. Pressure of a gas. Pressure of a gas is how much force is exerted, how much force is being put upon per unit area, per square foot, square yard, square, whatever it is, now in a certain defined area. How much force? Because you have a container, this gas is in a container, right? And these gas molecules are moving inside that container. And they hit the container and bounce back. And the force they hit with in a defined area, like PSI, when pumping a bicycle tire, pounds per square inch, when you pump your kids' bicycle tires. Okay. If you ride mountain bikes, okay, you're roughly running about between 50 to 60 PSI, pounds of pressure. So you pump the tire up with air until it reaches the point where those air molecules are hitting the surface of that ground. For every inch, 55 pounds of pressure are hitting every inch. That's what PSI means, pounds per square inch. Okay. If you ride a road bike, like I ride road bikes, that's how I enjoy racing road bikes. Road bikes run at 110 PSI. You have 110 pounds per square inch. If you ever blow a tire on a road bike, it sounds like a gun going off. It's extremely loud. There's a tremendous amount of pressure because those tires are very, very thin. A high amount of pressure, real thin tires, and you can go really fast that way. Okay, so there's less drag because it's pumped up so there's just a little part of that tire actually making contact with the road. But when one of those pops, there's a lot of force inside of those. Okay, double the force of most bikes. Most bikes run about 35 PSI, your normal kids' bicycles. That's what you pump them up to. But that's how you measure force. And that's how you measure pressure. Pressure is force per given area. How many times these molecules hit and bounce back in a certain area, how much force it puts on that tire wall or on this force shape of that container. Okay? Just like you blow a balloon. When you start blowing it up, it has a certain pressure into it, right? The more you blow, the larger that balloon gets, the more force you got to push with your mouth when you're blowing that balloon up, right? It takes more and more pressure because that is getting increased force coming back on you as you blow that balloon up. Okay? So that's how we measure pressure. Okay? We use it for all kinds of tools, oxygen tanks in hospitals for your patients. Okay? Also a certain amount of pressure that has to be overcome. Okay? And you can do conversions with it. You got common units of pressure are atmospheres. PSI, like we said. What else is there? A bar is another one. Kilopascals. Okay. These are all measurements of pressure. Okay, just so we measure temperature, we have centigrade, we have degrees centigrade, we do Fahrenheit, we have Kelvin. These are 10 ways you can convert between different pressures. It's still the same pressure. They're just different units you can use to express pressure. The most common we use in chemistry is atmospheres. That's what all of our formulas are going to be in atmospheres. Okay. And one atmosphere is equal to 760 millimeters of mercury. We use millimeters of mercury in doing blood pressure. Okay. Just how much force it takes to push up 1 millimeter of mercury. So one atmosphere is sea level, and it's equal to 760 millimeters of mercury. And you can do the conversions. We've done everything, all the other types of conversions. All right. All right, now we're gonna talk about some gas laws. Okay. So pressure times our volume is equal to a constant. Okay, so we multiply the pressure of what's in the gas container times its volume is going to equal a constant number. Okay, so if pressure increases, the volume has to decrease to keep the same number. Okay, so if you increase one, you decrease the other. They're indirectly proportional. Okay? Think of it this way: if you have a container with gas in it, okay, there's a certain amount of pressure. Say pressure equals 2, the volume is equal to 3 liters. Okay, if we take that volume and double it, so we take our volume, make it 6 liters, and keep the same amount of gas in it. Okay, the pressure is going to be 1. It's going to be half. We double the volume, we half the pressure. We do the same thing. It's inverse related. Because you can see, look at the pressure being exerted by these little dots here. There's a lot of dots. Now there's more less, the same amount of dots in a bigger area. Still less pressure. If you increase the volume, the pressure gets decreased. If you increase the pressure, the volume's going to get increased. Okay? And it's by the same number. So that leads to the formula P1 V1 equals P2 V2. It's equal to a constant. So you have an initial pressure and volume. It's going to equal the final pressure and volume. Make any changes. Just to prove that, let's use the same formula we did. Let's say we don't know that it was 6 liters that we increased to. Let's say we did not know the new volume. Let's say the question says you have a container, okay, there's a pressure of 2 atmospheres and a volume of 3 liters. We increase the volume to give us a pressure of 1 atmosphere. What volume do you have to increase it to? Okay. So you're looking for V2, our new volume, right? This is V2. So rearrange the formula. V2 equals P1 V1 divided by P2. This algebraic rearrange it. Out here, guys. What? What, man? No. Wow. Okay, that's your new volume, right? So V2 is equal to P1. P1 was 2 atmospheres. Okay. Volume 1 was 3 liters. And P2 was 1 atmosphere. Atmospheres cancel, we're left with liters. 3 times 2 equals 6, just like we said before. Okay. Now, they're not going to be that simple. I guarantee we'll make it a little more complicated. We have to, right? All right, but this is what's called Boyle's Law. Like I said, you do not have to memorize any of these. You'll have them all in the book. You can look them all up. And they're all going to be related to the ideal gas law, which we're going to get to in a little bit. We're going to kind of derive that from all these different relationships. Because remember, we have pressure. We have 4 different relationships with gases. We have pressure, which we can change. We have volume, which we can change. We can change the amount of gas particles, so the number of moles. We can change the moles inside the container. You know, let some out, put some in. Just like with the bicycle, you put more air in the tube. And temperature. I mean, think about temperature for just a second. If we increase the temperature in this container, we make it hotter. Those little gas molecules are going to move faster, right? You're increasing temperature, they're going to move faster. When move faster, they're going to hit the wall harder. They're going to increase the pressure. So everything's going to be related. We have 4 variables that you're going to have to deal with in gases. We have pressure, we have volume, we have number of moles, which is N, and we have temperature. Those are the 4 values that can be affected in our gas laws. And we have different relationships, but they're all going to be derived from one formula, from your ideal gas law. And we'll get into that. You might have heard it, you might have seen this before in high school chemistry, but PV equals nRT. That's where all our gas laws derive from. Okay, that's your main one. Okay. You can see pressure and volume have an inverse relationship. Pressure and temperature have a direct relationship. Volume and temperature have a direct relationship according to that equation. So I got pressure, volume, N, and then R. This is your ideal gas constant. Okay, and R is equal to 0.08206 liters atmospheres per mole per Kelvin.
Should be out in 2
Okay,
weeks.
that's our relationship.
Should be out in 2
Okay.
weeks. Should be out in 2 weeks.
Who?
What's your name? Abronia.
Okay. All right, so that's our relationship there. So we're gonna get into that in a little bit. That's just where we're heading. So don't panic on that one yet. But the one I want you to understand is pressure times volume is a constant. So P1 V1 has to equal P2 V2. Okay. So let's give you an example of a question here using this one. What's the initial pressure in a container? So you want to find the initial pressure in a container that has a volume of 3.0 liters. Okay. If the pressure now, okay, what has gone to is we have a pressure of 18 atmospheres, and the size of the container is 6.0 liters. What was the initial pressure in the container? So what was the initial pressure in the container at 3 liters has now been moved to a 6-liter container, and that is 18 atmospheres of pressure. That's the type of question you see on final. Okay. So all you have to do is identify your variables. This is P1, V1, P2, V2. P1 equals what? P1 is what you're looking for, the initial pressure. The initial volume is 3 liters. P2 is the pressure of the second container, which is 18 atmospheres. There are pressures in atmospheres. The volume is in liters, milliliters, whatever volume you want to measure it in, square inches. And volume 2 is 6 liters. So now you get all good. This is how you do all the gas problems to make it easy. On the side, write down all your variables. Okay, so we're not changing the number of moles. That's constant. That's not getting affected. We're not changing temperature. When we change the molar temperature, then it gets a little more complex of a formula. But right now, all we're changing is the pressure and the volume. And that's related by our formula. So we're looking for P1. So solve our equation for P1. P1 equals P2 V2. And let's divide both sides by V1. And then plug your values in. P2 is 18 atmospheres. V2 is 6 liters. V1 is 3 liters. And then double check to make sure your units cancel. Liters cancel, and you're left with atmospheres, which is a measurement of pressure, which is what you're looking for. So 18 times 6 divided by 3, okay, is 36 atmospheres. That's the initial pressure. So in order to meet those requirements where your final pressure is 18 atmospheres in a 6-liter container, if it started off in a 3-liter container, the pressure had to be 36 atmospheres. Does that make sense? Yes, no, maybe?
Yeah.
Okay, because we're gonna make it harder. Of course, right?
Right.
Gotta challenge you guys.
This class always gets increasingly harder, so we're used to it.
That's true. It does. That we start off simple. This is pretty good. It's 4 variables. We give you 3 and you solve for 1. The rest of them aren't too hard, but everything's gonna go to that one formula that we talked about, the ideal gas law. Everything's gonna boil down to that. But this is called Boyle's law. We also have Charles' law. Charles' law is between volume and temperature. And if we remember, let's click on check my board here. If we remembered our PV equals nRT, we saw pressure and volume were indirectly related because one up, one has to go down. Now pressure or volume and temperature, Charles' law is volume and temperature. So volume and temperature are going to be directly related. If one goes up, the other goes up. So this is going to be volume 1 over temperature 1. is going to equal volume 2 over temperature 2. Okay? Those are directly related. In other words, if I increase volume 1, I have to increase T1 to keep it the same. If I increase the volume, because think of it this way. We got a gas in our little balloon or square container here, and here's our gas. If I increase the volume and the pressure has to stay the same, what has happened to the temperature? I've got to increase the temperature to make these molecules move faster to hit with the same pressure because there's a bigger volume out for them to hit. And that's all it says. So pressure and volume are inverse related. Volume and temperature are directly related because they're the same on both sides of this ideal gas law. It tells you which one's directly related, which one's inversely related. Okay, so let's do an example with one or volume. Say you have a container or initial. We're going to take an initial volume of a gas is going to be 6 liters, 6.5 liters. Okay, initial temperature. Let's
Show
put
in
it
the house
at.
Wednesday, the other house.
Cool, thanks. Let's say a temperature of 23 degrees centigrade. That's what we're starting at. So we transfer this to a container that's actually 13.8, I make bigger numbers, liters. Okay. What temperature is the gas going to be at? Okay. You want to know what temperature is that gas going to have to be at? I put a 13-liter container. So we're taking oxygen from a compressed container, which we have a little pump down, make oxygen for our patients. We're going to put that pressure oxygen into a bigger cylinder. We don't know what temperature it's going to be. Because don't forget, if we increase the volume, we put it into a bigger tank, the temperature is going to increase to keep that pressure the same with the gauge on top we have. And you don't want to increase it to a temperature that cannot be tolerated by your patient's lungs. I think 23 degrees centigrade is roughly room temperature. Let's say we dump it into a bigger container for our patients, and we keep that same pressure with our valve on it, what's going to happen? So look at our formula. V1 over T1 equals V2 over T2. So we're given V1 is equal to, our initial volume is 6.5 liters. Our initial temperature, we start at 23 degrees centigrade. Okay. When we do these, everything is, let me go back just a second. All our temperatures have to be in Kelvin because we're related to Kelvin. That's our gas laws are written. So everything has to be in Kelvin. Okay. Our natural gas constant here is in measurements in Kelvin. So when we do these exercises, all temperatures have to be converted to Kelvin before we put them in our simulator. So we have V1, T1, V2, and T2. And T2 is what we're looking for, and V2 is 13.8 liters. And T1 is, remember, degrees centigrade plus 273 equals Kelvin. Okay. So we take our T1 is 273 plus 23, 296 Kelvin. Okay. So we're dealing with gas laws. Everything is recorded in Kelvin. So we go back to our formula. This V1 over V2, V1 over T1 equals V2 over T2. And we're looking for T2, right? So T2, okay, rearranging it algebraically, multiply V2 is going to equal V2 times T1 divided by V1. That's rearrange it, because we got to bring this up to here. That's T2. Multiply both sides by T1, bring it over here, and then V1 has to come down to the bottom. Just rearrange it algebraically. Okay. So volume 2 is equal to 13.8 liters. T1 is 296 Kelvin. And V1 was our initial volume of 6.5 liters. And then do the math. Where's my cell phone? Hopefully it's charged up a little bit. Yeah. All right, let's find our calculator. And you take 13.8 times 296. You gotta start writing neater. Divided by 6.5. and it comes out to 628 or 600, yeah, 628.4 Kelvin. Okay. Then to get, if you want your answer in degrees centigrade, depends what the question asks. If it's in degrees centigrade, it's going to be 628, and you're going to subtract 273. And that's going to equal 355 degrees centigrade. Okay. So do you want to move your Parsons container, okay, from 6.5 to 13.8 liters at the same pressure? All right, the lungs are not going to tolerate 355 degrees centigrade temperature gas. It's going to destroy their lungs. It's going to burn them. Okay? So you got to be really careful doing your calculations with this. Because if you change the size of your container, you're going to change the temperature if the pressure remains constant, according to Charles' law, which is V1 over T1 equals V2 over T2. Okay. That's our temperature volume. Okay, we did a couple of those in the books. All right, let's do one from your book here. It says the gas. Okay, it says the gas occupies a volume of 15.2 liters. So this is your gas. Gas occupies a volume of 15.2 liters. Okay, at 25 degrees centigrade. All right, that's what you're given. At what temperature will this gas expand to a volume of 30.4 liters? So it's going to go to a new volume of 30.4 liters. Okay. And you want to know what temperature would that gas be at? Okay. Now it should tell you that the temperature remains constant. Yeah, I'll tell you that in the equation. So you know volume and temperature are your relations. So you know your formula. V1 over T1 equals V2 over T2. Because the pressure's not changing, the mole's not changing. And like I said, you don't have to memorize these equations. You'll have them all on, they're all in your data packet. They'll be all on in your book, or you can look at during your final exam. But you have to know how to use them. I'm not going to give you simple things you just plug in. You have to think, rearrange equations, and know which ones you use. So know how to use these. Don't sit there and memorize equations. That's not going to do any good. But learn how to use them.
The timer makes you nervous.
What's that?
The timer makes us really nervous.
Don't worry about the timer. I know. I know it's hard. I've been in the same situation. But the best thing to do is, what's
You
that?
freeze. I froze.
I know. Just study the best you can and realize the more you practice of using it and not memorizing it, the better off you'll be. Okay. But I know a lot of people don't take tests very well. That's why I have a lot of homework and a lot of labs. You can use those to build up your points too. Because I know a lot of people don't take tests very well.
So if you get a poor score on your final and your midterm, but you do all of your homework, you can still survive.
Oh, definitely.
Okay. Okay.
Well, the average of the final wasn't very high. So I mean, I'll get all the statistics for by Wednesday. I'll do the calc. I haven't had a chance to do it this weekend yet.
Okay. Because I'm trying to swim with the homework.
Okay.
Same here.
Yeah,
I'm doing the exact same thing.
that's how most people do it. There's nothing wrong with that. That's why I set up that way. Okay. But still, if you do really well in the midterm and final, you guarantee yourself really good grades. Okay. But you still keep up and go right along with everything else. And I'll get all the statistics for the midterm for you by Wednesday. All right. So now we've got, what do we got? We've got our initial one at V1 was 15.2 liters. T1 is 25 degrees centigrade, and that's equal to 273 plus 25 equals 298 Kelvin. And then V2 is equal to 30 0.4 liters. T2 is equal to, well, we don't know. So again, rearrange our equation. We've got T2 equals V2 T1 divided by V1. And plug your numbers in. V1 is 15.2 liters. Now be careful too. If one of the volumes in liters, one's in milliliters, you got to convert. You have to have everything the same, so it cancels. Got to make sure temperature in Kelvin. You got to make sure the volume is the same, whether it's liters, milliliters, nanometer, nanoliters, whatever. Just make sure it's all the same. Ounces. If it's the same, it's going to work. T1 is 298 Kelvin. And V1 is 50. Did I put the wrong one in here? I sure did. This should have been V2, right? V2 is 30.4 liters. Somebody should have stopped me. 30. I was just seeing if you guys could catch that. I'm just kidding. 30.4 liters. It's very easy to make mistakes. That's why work with me, do them as you go along. Make your mistakes now. Make mistakes now, you won't make the same ones on the midterm or the final. So V2 is equal to 30.4 liters. T1 was 298 divided by V1, which is 15.2 liters. Okay, and want your answer in Kelvin and Celsius. Where's my phone? All right, so 30, do the math. 30.4 liters times 298 divided by 15.2. Comes out to 596 Kelvin, which minus 273 comes out to 323 degrees centigrade. So this is in Kelvin. And 323 degrees centigrade. If you put 596 degrees Kelvin, do you think I'm going to mark it wrong?
No.
Yes, I will.
Kelvin isn't.
There's no such thing as degrees Kelvin. Kelvin is not a temperature. Kelvin is a movement of energy.
Can I get extra credit for that?
Do not ever put degree Kelvin.
I remembered that as your pet peeve.
That's right. That is it. Degree centigrade, degree Fahrenheit, but it is Kelvin, not degree Kelvin. It's like when patients come in and tell me they have TMJ. But yes, you have TMJ. Everybody has a TMJ. You have TMJ dysfunction. You have TMJ pain. Yeah. But you can't come and say, like that's like coming into your medical clinic and say, I have a temperature. Yeah, you got a temperature. And you can have an elevated temperature. You have a fever, but everybody has a temperature. Everybody has a TMJ. Kelvin is not centigrade, is not degrees. All right. Everybody understand so far?
I don't get why you subtracted 273 from.
Because they wanted the answer in Kelvin and centigrade. Remember a formula for converting. Degrees centigrade equals 273. I made the 3 that work backwards. Hold on, I was going to put a point there. 273.15 to be accurate. Okay. I'm writing this backwards here. Degrees centigrade is going to equal, okay. I'll make it easier. Kelvin equals your degrees centigrade plus 273.15. Okay. So degrees centigrade, so to convert degrees centigrade to Kelvin, you add 273. To go the other way, you got degrees centigrade is going to equal Kelvin minus 273.15. That's where this came from. So that's just our conversion.
Okay.
If you have degrees centigrade, you want to go to Kelvin, you add 273. If you have Kelvin, to go back to degrees centigrade, you subtract 273.
Okay. Got it. Thank you.
Oh, no problem. Okay. Now, let's make this a little bit harder, okay? Since we all got this down pat, it's pretty simple, right? We're going to do what's called the combined gas law. We're going to use pressure, volume, and temperature all together now. So say we're going to change pressure, volume, and temperature. Well, all that's going to be consistent now, the number of moles is staying the same. So remember, pressure times volume was a constant, and both ones divided by temperature. So P1 V1 divided by T1 equals P2 V2 divided by T2. Okay. Pressure and volume are indirectly related. So when one goes up, the other goes down. Volume and temperature are directly related. When one goes up, the other goes up. So that's how they're set up. So one's directly related, one's indirectly related. Okay. So pressure and volume have an indirect relationship. Volume and temperature have a direct relationship. So all we're doing now is just adding another variable. And again, it's all coming back to this point we're going to get to, PV equals nRT, where R is a constant. Okay, so in other words, you can write this as PV over NT equals R, because R is always a constant, so that never changes. So here's your relationship right here. And we can add moles to it in a little bit too. We can put that on the bottom also. So everything's going to be based upon this formula. Okay, like I said, you don't have to learn how to derive it. You'll always be able to go back and look these up in your textbook for any questions. So if you ever have a question and it says the pressure, volume, and temperature change, and the number of moles are constant, we're going to use this. Okay. Now, we're going to end up with this formula, and we're going to end up with this formula. Most students have a real hard time choosing when to use these different formulas. If there's a change, you use this. If there is no change, if it's constant, you use this. Okay? So if there's a change, you're going to set up initial and final, or 1 and 2. If there's no change, you're just going to go with your regular P equals nRT. And we'll get into those also a little bit here. Okay? So this is our new formula. This is called the combined gas law, because we're combining Charles and Bo's law together. So that's a combined gas law. All right, let's pick one from your book and see what they want to do here. I don't want to do kilopascals, so let's do atmospheres. All right, we'll do example from your book, 10.5. How's that sound? Why is it only this? I don't like that one either. Let's make up our own question, because that's not going to use all the variables. We're going to cancel those out. And I want to use all of them for now to get you used to it. So let's say you're entering the laboratory and you come across this mysterious box. This box has a gas inside the box. The gas has an initial pressure of 5 atmospheres. So you've got this gas in a box, and you measure the pressure in the box. Okay, gas in the box. Not like Jack in the box, but gas in the box. And you measure the pressure in the box at 5.3 atmospheres. Okay, the size of the box is, say, 6.8 liters. And the temperature in the box, you say you measure the temperature of it, and the temperature is at 24 degrees centigrade. Okay, now you take that box and we increase the temperature to, say, we're going to increase the temperature to 29 degrees centigrade. And we're going to crank the pressure up to, say, 10.5 atmospheres. You want to know what size this box is going to expand to. Okay, the box is made out of plastic and it can, or rubber, and it can expand. So you want to know how big the box has expanded under those conditions. How big is the box now? Does that make sense?
Yeah.
Yes.
Okay, so that's just the wording of it. So we go back, we want P1, V1, T1. The initial pressure is 5.3 atmospheres. Again, just make your little table, it's so much easier. The initial volume of the box was 6.8 liters. And the initial temperature was 24, and we're going to add 273 to that to turn into Kelvin. So 273, 297. 297 Kelvin. That's your initial starting points. And we've got P2, V2, T2. We know the pressure is 10.5 atmospheres. We know the volume is, that's what we want to look for. Here's our question mark. And we know the temperature is 29, so 273, 302, right? 302 Kelvin. All right, we got all our variables. So we got to solve this equation here for V2. V2 is equal to P1 V1 equal to V2 is equal to P1 V1 T2 divided by P1, and where am I at? V2 divided by P2. Okay, so V2 equals P1 V1 T2 divided by T1 P2. Okay, just algebraic rearranging it, and then we just plug our values in. P1 is 5.3 atmospheres. Oh, come on, right better than that. Okay. 5.3 atmospheres. And V1 is 6.8 liters. And T2 is 302 Kelvin. Divided by, and T1 is 297 Kelvin. And P2 is 10.5 atmospheres. Okay, everybody see where the numbers came from?
Yeah.
Okay, and we just play in the calculator then. We have, where'd the calculator go? 5.3 times 6.8 times 302. Divide 297, divide 10.5 equals 3.49. And what units are left? We have Kelvin cancels, atmosphere cancels, we're left with liters. Okay, so the box has shrunk to 3.49 liters. So if you're given 5 of the variables, you can solve for the 6th one. Okay, so again, going back to our combined gas law. Okay, there, let me change the page here. We got that. So our combined gas law was this. Now, if temperature doesn't change, that means T1 and T2 are equal, right? That means temperature is constant, so P1 V1 equals P2 V2. Does that look familiar?
Yes.
Yeah, if pressure is constant, pressure doesn't change. V1 over T1 equals V2 over T2. Does that look familiar? That's the same law we just used too. Okay, so if any of these variables are constant, you derive the other equations. And that's how we use it, just like that. Okay. Then we got the combined gas law, Charles law, Boyle's law, all that good stuff. Then we got Avogadro's law, where we're going to put in the number of moles. So basically, all that's going to say is P1 V1 over N1 T1 equals P2 V2 over N2 T2. All the same, and that's just the number of moles now. N is the number of moles. Okay. We have something called at STP conditions. STP is standard temperature and pressure. Okay, doesn't stand for your gasoline additive STP. Okay, STP is standard temperature and pressure. So STP means your temperature is equal to 0 degrees centigrade, which is 273 Kelvin, and your pressure is equal to 1 atmosphere. Okay. Now, we use this to convert what's called our molar volume, or the volume of any mole of any gas, at STP conditions. Okay, so you're given, we look at this equation here. Okay, so we know P1, V1, N1, T1 is equal to a constant. Let's say our constant's K. So pressure times volume over the number of moles times temperature equals a constant. Okay, that's when you set them equal to each other at different conditions. You know, if we have a gas and we're putting it at STP conditions. Okay, so let me clear this so we can come back to this. So our STP means temperature equals 273 Kelvin, right? 0 degrees centigrade, and pressure equals 1 atmosphere. So any gas, if we have 1 mole of any gas, we know the volume has to be 22.4 liters, no matter what the gas is. And we'll prove it to you. Because, where's our pressure? Pressure, volume, and T equals our constant. Okay, so we're going to solve for temperature. Okay, we know the temperature, know the pressure. So the volume is going to equal N over T divided by P. Okay, we're going to set our volume equal to our constant. Okay, so we know the number of moles is 1. We said 1 mole of any gas at STP conditions. Temperature is 273 Kelvin. Okay, and pressure is 1 atmosphere. 273 on 22.4 liters. I'm missing out my constant here. Let me back up a little bit. Okay. Like I said, if there's no changes, we use ideal gas law, which we said was PV equals nRT. All right. There we go. It's kind of going off on a little bit there. So PV equals nRT is our ideal gas law. All right. So I said any gas, 1 mole of any gas, has a volume of 22.4 liters. So whenever you have 1 mole of something at STP conditions, it's going to be 22.4 liters. Okay. So let's rearrange this to solve for our volume. Volume equals nRT over the pressure. N is 1. It's 1 mole. R is 0.08206, and the 0.206 liters, atmospheres per mole per Kelvin. Those are just the units. Liters, atmospheres divided by moles in Kelvin times the temperature. And the temperature you said was 273 Kelvin. Okay, and the pressure is 1 atmosphere. And you do the calculation, that comes out to 22.4 liters. So any gas at STP conditions, which is 1 atmosphere and 0 degrees centigrade, 1 mole of any gas is going to have a volume equal to 22.4 liters, no matter what the gas is. This is the reason we use Kelvin also. See where it said 0 degrees centigrade? Okay, temperature 0 degrees centigrade. Can you ever have 0 Kelvin? No.
No.
You can never have 0 Kelvin. All motion stops, which means all matter will condense because electrons are in motion around the atom. Remember they got this huge thing like the football stadium where a P is the size of the nucleus and the electrons are flying around it we talked about. If motion stops, all that collapses. So the Earth becomes the size of a P basically. Everything would collapse. So 0 degrees centigrade can occur, 0 Kelvin can never occur. You can approach 0 Kelvin, slowing things down, but you can never achieve it. So all of our gas laws, if you had a 0 up here, what does that number become? It's going to become 0, right? So you can never have a 0 for your temperature. That's why you have to convert everything into Kelvin. Okay? So our molar constant for any gas is going to have 22.4 liters at STP conditions, standard temperature and pressure. 0 centigrade, 1 atmosphere pressure. Okay, so this is our ideal gas law. And we use that when things don't change. We're not changing anything. We have certain set conditions. Let's go to, so remember it's PV equals nRT. P is pressure, V is volume, N is moles, R is the ideal gas constant, and T is temperature in Kelvin. Okay. So let's say we have, let's centigrade pressure. Okay, we solved that for our ideal gas law. Let's change it. I want to do conversions of that. So let's say we have let's say you're at a party and they bring out nitrous balloons. Okay, you have these nitrous balloons floating around. Okay, inside the balloon, there's going to be a certain pressure. The volume of the balloon is 3 liters. So these balloons are 3 liters. You have 2.8 moles of nitrous oxide inside each balloon. And the temperature in the balloon is room temperature, which is roughly 25 degrees centigrade. Okay, what is the pressure of nitrous inside each balloon? Which means how fast it's going to go in your lungs when you suck on these nitrous balloons, right? All right, so to do that, now you're given a set of conditions. Nothing's changing. You're not changing temperature. You're not changing the volume. You're not changing the number of moles. You're not changing the pressure. So there's no change. So there's no P1 V1 equals P2 V2. You don't use that because there's no change. If there's no change, you use PV equals nRT. And we're looking for, let's see, pressure. We said equals, that's what we're looking for. Volume of each balloon is 3.0 liters. N is equal to 2.8 moles. And R is a constant. T is equal to, we said 25 degrees centigrade, which is 273, 298 Kelvin. Okay, we got our values. So solve this for pressure. Pressure is going to equal nRT divided by V. Okay, that's really good. Everybody see why I'm using this one and not P1 V1 over T1 equals P2 V2 over T2. Everybody see where we're not, everybody understand why I don't use that one?
Yeah, I think so. Because there's no change, right?
Perfect, because there's no change. You have a pressure, you've got a volume, you've got a number of moles, and you got a temperature. Nothing's changing. If something's changing, you gotta do a comparison. Then you gotta do one of your gas laws, Boyle's, Charles, or combined gas law. And that's the biggest hang up most students get is when to use this one and when to use this one. This one is no change. Okay. Everything's given at units and you're not changing the conditions of any of them. Pressure, volume, temperature are all one measurement. You're not changing that measurement. So N is equal to 0.08206 liters, atmospheres per mole per Kelvin. R, that's R. N was the number of moles, which is, how many moles does it have? 2.8 moles. And temperature was 298 Kelvin, running out of room. And the volume was 3.0 liters. Now, liters cancel. Moles, this is per mole, this is moles, that cancels. Kelvin per Kelvin, Kelvin cancels. And what we're left with is atmospheres, which is pressure, which is what we want. So chances are we set it up right. So we take 0.08206, 0.08206 times 2.8 times 298 divided by 3 equals 22.8 atmospheres. That's how much pressure is in each nitrous balloon at the party, if you measured out the number of moles correctly. And that's how we use ideal gas solve. Okay. Okay, let's do one more with that. Let's say, let's go back up here. Let's get rid of that one. All right, let's say we have a gas cylinder at the hospital. Okay. Let's say these gas, what are gas cylinders at the hospital about? They're 5 liter containers. So this is a 5 liter container of oxygen. Say there's 86.2 grams of oxygen in there. Say the temperature in the container is a little higher than room temperature. Say it's about 30 degrees. 30.0 degrees centigrade. Let me get a little meter so we can see what it is. 30.0 degrees centigrade. Okay. What's the pressure inside the container? Okay. So we're looking for pressure. So are any of the variables changing? Yes or no?
No.
Okay, so what are we going to use? Right? So let's make a little chart. Always make a little chart. Pressure, volume, and RT. Pressure we know is, that's what we're looking for. Volume is 5 liters. Number of moles is, we don't know. But we can figure it out. We've got 86 point, gosh, I can't write that really neat. 86.2 grams of oxygen. And oxygen is, look on the periodic table, there's 2 oxygens, so 16, 16 is 32 grams per mole. So 86 divided by 32, 86.2, sorry. 86.2 divided by 32 equals 2.69 moles of oxygen. Now we got moles. And R we know is 0.08206, and temperature is 30 degrees centigrade. And that's equal to 303 Kelvin. You got all our numbers. So we're looking for pressure. So pressure equals nRT divided by V. N is the number of moles, 2.69 moles. R is 0.8206, right? Keep on blank on it. 206 liters, atmospheres per mole per Kelvin. Those are just units of it. Temperature is 303 Kelvin. And volume is, where's our volume? 5 liters. Make sure your units cancel. Liters cancel. Moles cancel. Kelvin cancels. You're left with atmospheres, which is pressure. This is what we want. Okay, so we take those numbers, multiply top, divide by bottom. We have got, clear that, 2.69 times 0.08206 times 303 divided by 5. It's going to equal 13.4 atmospheres of pressure. So 13 times the noun pressure of oxygen at sea level, which is about right. So when you open the valve, pressure is going to flow into the patient's lung. and about 13 times the normal pressure that fill their lungs with oxygen. Okay. So those are your formulas. You have a combined gas law, P1V1 over T1 equals P2V2 over T2. And you have the ideal gas law, PV equals nRT. Pressure times volume equals the number of moles times the ideal gas constant times the temperature. Okay. So far, so good.
Yeah.
All right, let's talk about law of partial pressures of gases. The law of partial pressure simply says, we're still on section 10.4. So we have a new law now. This is the law of partial pressures. The law of partial pressure says that every gas is going to behave as if the other gases weren't present. Because there's so much space between gases, okay? Everything's going to behave ideally. Nothing's going to interfere with other gases. So if we have a container, okay, and we put in a partial pressure of oxygen equal to 10, a partial pressure of nitrogen equal to 15, and a partial pressure of carbon dioxide equal to 5, the pressure inside this container is going to be 30. We're just going to add those together. They're all going to exist as if the other gas wasn't present. So oxygen is going to put a force of 10 atmospheres, nitrogen is going to put a force of 15, and carbon dioxide is going to put a pressure of 5. So the total pressure in the container is as each one is acting independently. Because gas has so much space in between them, there's going to be no interaction, no slowing down, nothing's going to bother anybody else. So that's how law of partial pressures say that if you mix gases together, the total pressure in the container is going to be the summation of each gas as if they were individually. That's it. I know I can't make this one any harder. Sorry. Okay. So if we have a container, in this container, we have 15 atmospheres pressure. I have 3 gases in this container. I have carbon dioxide, I have oxygen, and I have chlorine gas. Okay. The partial pressure of carbon dioxide is 5. The partial pressure of oxygen is 8. What's the partial pressure of chlorine gas? What's the partial pressure of chlorine gas? The total is 15. Partial pressure of CO2 is 5. Partial oxygen is 8. The partial pressure, what's that?
2.
2. Bingo. Perfect. Has to be. Because the pressures have to equal the total in the container. That's it. I can't make this one any harder, guys. You just have to add them together. All the gas has up to the total. Okay. Now this law, this applies for most conditions. The only time it starts to break down is under very, very, very high pressures, extremely high pressures. What extremely high pressures do is they push these gas molecules closer and closer and closer until now you can have some interaction between them because it's being pushed really close together. So very high pressures. I mean, extremely high pressures, nothing we normally deal with, okay? And very, very low temperatures. Those two conditions, the ideal gas laws break down. Because again, you're taking that pressure and you're squeezing, squeezing, and you're gonna force those to have interactions with each other. I mean, you're talking extremely high pressures. I mean, thousands and thousands of atmospheric pressures. Nothing we normally deal with. And very, very low temperatures, like approaching 0 Kelvin. Because then everything starts to slow down. And if they slow down, then they can start passing each other and interacting with each other. Then they can have some polar forces being involved. So under extremely high pressures and extremely low temperatures, these laws do tend to break down a little bit. But for the most part, for everything we're going to be doing, okay, all these laws are going to apply. the laws of partial pressures, Charles law, Boyle's law, and ideal gas law, and part law and the combined gas law. All these laws apply under our conditions. Okay, these are the only times, just for you to know that they do tend to break down. Very high pressure, very low temperature. All right, let's go. That's our molecular view of gases. They're molecules that move in a container. So let's try one of these exercises here on your book. Let's say, how do these things affect the pressure of a gas? So how does it affect the pressure of the gas? Okay, decrease in temperature. Decrease in temperature does what to the pressure? Increase it, decrease it, or doesn't affect it at all? If you lower the temperature, what happens to the pressure? Don't change anything else, just the temperature. What's it going to do to the pressure?
Nothing.
We'll do something. You're in a container. You got these molecules flying around, moving in these directions. Okay. I lower the temperature. What happens to the speed of those molecules if I lower the temperature?
Will it decrease?
Perfect. It decreases the speed because you're not heating them up. There's no kinetic energy anymore. So they start to slow down. If they slow down, they hit the side of the container with less force because you're going slower. So when you lower the temperature, I decrease the pressure because they're not moving as fast. Okay. What if I decrease the volume? I take that volume and I make the volume smaller. What happens to my pressure? So I take these molecules and I put it in this volume. All the same number of molecules. What happens to the pressure? You get much more collisions with the side, right? Because there's less area. So it's going to take, that pressure is going to be greater per that unit area. So it's going to increase the pressure. Okay? Because there's less volume. It's because the molecules are going to hit the side more often and create more pressure. And if we decrease the number of moles of gas, we take gas out of the system, what happens to the pressure? Think of your child's bicycle. If you take air out of the bicycle tire, what happens to the pressure?
Decreases.
Decreases. Perfect. Think of it in terms of things you know. Okay. So decrease in temperature decreases the pressure. Decrease the volume is going to increase the pressure. Puts a small amount. Decrease the number of moles, take air out of the system, we're going to decrease the pressure. Perfect. Okay, diffusion and effusion. Okay. This is how a gas molecule moves through a given space. There's your diffusion and your effusion, which way it's going to move. Okay, so basically all this says is lighter particles, lighter gas particles are going to move faster. They're going to diffuse or going to move across a certain area faster. Heavier gas particles are going to move slower because it's going to take more energy to push them across. That's it. That's effusion and diffusion. Okay, you've got a lighter particle, it's going to move faster. Got a heavier particle, it's going to move slower. It takes more energy to push it. Okay, so they're gonna mix faster if they are lighter particles. Okay. So if you're gonna mix, let's say we have two balloons, and we're gonna mix them together. One has methane gas, and one has oxygen gas. Okay, another two balloons. One has propane, C3H8, and one has carbon dioxide gas. We mix those together. Which of these two systems are going to mix together faster? Okay. Which ones are lighter? This is 3 carbons, 8 hydrogen. This is 1 carbon. This is 2 oxygens and 1 carbon, there's only 2 oxygens. So these are much lighter. So these are gonna mix together faster. They're gonna move faster. They're gonna mix or effuse together quicker. Okay? The lighter it is, the faster it's gonna move. The heavier it is, the slower it's gonna move. So tell which one's gonna mix quicker. All right, one more section. This is on stoichiometry. Didn't you guys all like stoichiometry? How you can do it? Now we can do that with gases too. Now we're going to use that with our PV equals nRT. Hey, Walter. All right, let's see what kind of questions they have here. You can have one. All right, let's do one of the problems in your book. Example 10.9 or 10.10. Which one we want to do? Let's do 10.9. In the fermentation of glucose, so making of glucose, how many moles of carbon dioxide are produced for each kilogram of glucose that reacts? Right, reaction takes place in a sealed container. 8.1 liters, temperature 20 degrees centigrade. Find the pressure of the carbon dioxide gas inside the container. Okay, so the fermentation process is glucose. You're going to form C6H12O6. C6H12O6. Okay, that's your sugar. Is going to go to C2H6O. Okay, breaking it down to alcohol and carbon dioxide. Carbon dioxide gas. And this is what the question is telling you. It tells you the what does it tell you here? It wants to know how much moles of carbon dioxide. So I'm going to find how many moles of carbon dioxide are produced for every kilogram of glucose. So 1 kilogram of glucose takes place in a sealed container. Okay, we can do that. And it wants to know how many, what is the pressure of carbon dioxide? You want to know the pressure of CO2 if the container is 8.10 liters at a temperature of 21 degrees centigrade. I know there's a lot here right now. Okay, so it wants to know if you have 1 kilogram of sugar, and this is solid sugar, and this produces a liquid alcohol. This is what gives you your fermentation process, and the CO2 gas. This is how you ferment champagne. All the bubbles in champagne are carbon dioxide. This is how you get it. They add sugars. You allow the sugar to ferment, turn into alcohol and CO2. The CO2 goes up, and that's your pressure. That's when you pop a champagne cork, it shoots across the room because of the pressure in CO2. And it wants to tell you, it wants you to know how much, what's the pressure in CO2 of the sugar with 1 kilogram reacts to form your alcohol and your CO2. Okay, so it wants to find the pressure of CO2. That's what we're looking for. Okay. Now, are we going to use PV equals nRT, or use P1 V1 over T1 equals P2 V2 over T2? Which one are you going to use? Are we changing the pressure? Someone say no. Are we changing the liter? It's 8.1. No. Are we changing the temperature?
No.
No. Are we changing the number of moles? No, we're just producing moles. So we're going to use PV equals nRT. Okay, we're looking for the pressure. We know the volume. Whoa, what happened here? Okay, we know the volume. We can calculate the number of moles right here. We know R, and we know the temperature. So let's calculate the number of moles. So we use our regular equation. What's the first step I always tell you? You have to do. You have to
Balance
balance
your equation.
Equation not balanced, it doesn't mean jack diddly. Doesn't mean anything. So is it balanced? No. All right, we got 6. Where are we at?
6 carbons.
6 carbons on the left, and we have 3 on the right, right? So looking at that, carbon's going to be split. So let's do hydrogens first. So I got 12 hydrogens. And to make the other side say 12, I have to put a 2 right here, right? That'll give me 12 hydrogens to balance my hydrogens. And let's balance our carbons next. So there's 4. I put a 2 here to make 6. And let's check our oxygens. I have 6 on the left. How many do I have on the right?
12.
Not oxygens. I have 2 on the first one, and I have 4 on the second, so I have 6. So I have 6 carbons on the left, 6 carbons on the right, 12 hydrogens on the left, 12 on the right, 6 oxygen on the left, 6 on the right. We're balanced. So let's do the math. We're starting with 1 kilogram of glucose. So I got 1 kilogram. I have to convert that into grams. Kilogram is 1,000 grams. Okay, now I got grams. In grams, I have to go to moles. You got to go to moles. You got to get to moles to use your chemical equation. So I have 6 carbon, 12 hydrogen, 6 oxygen. So 6 carbon is 72. What's 12 times 6? 72, right? Yeah. And I have 12 hydrogens. And I have 6 oxygens. So 16, 32, 64, 94. Let me get my calculator out. I don't want to make a mistake on you guys here. So 6 times 16 equals 96. So 6, 8, 10, 8, 9, 18, 180 grams per mole. Let me just double check. Carbon is 12 times 6, 72, 12, 96. Yeah, that looks right. Okay, 180 grams per mole. So that's the molecular weight of glucose. So glucose is 180 grams per mole. Okay, so I got moles of glucose, C6, H12, O6. And I'm going to moles of CO2. What's the ratio? How many moles of CO2 are a balanced chemical equation? What's in front of the CO2?
2.
2. And how many moles of glucose? 1, right? So now I got moles of CO2. Oh, that's what I want, actually. I don't have to go back to grams. Okay. So let's take these numbers here. And let's say we have 10 to the third. We have 2 on the top. Divided by 180. Comes out to that. And I have times 10 to the third. So move the decimal point 3 places. I have 1, 2, 3, 11.1 moles of CO2. Is that everybody else got? 11.1 moles, 1,000. It's actually, do it either 2,000 divided by 180. That's what it actually comes out to. So let's double check it here. Divided by 180 equals 11.11. Perfect. Got it. All right. So now we got our moles of CO2. So now we have everything we need. We're looking for pressure. So pressure equals nRT divided by V. Number of moles we calculated at 11.1 moles of CO2. R is 0.08206 liters atmospheres per mole per Kelvin. And temperature is, we said 21 degrees centigrade. 21 degrees centigrade, at 273, 294, right? 273, 294 Kelvin. Comes out to 294 Kelvin. All that divided by the volume of container, which is 8.10 liters. So the pressure inside the container as we are burning our sugar to produce alcohol and CO2. And you use different types of sugars or different concentrations to produce bourbon or scotch or champagne, all that. Even with soft drinks. With soft drinks, you're not making alcohol, but you're producing CO2 as your byproduct. And that's what gives you the gas. So the same bubbles in champagne are the same bubbles in Coca-Cola. That's what gives you the pressure when you open that can and it pops and fizzes.
You know where mom is?
All right, so we take 11.1 moles and times 0.08206 times 294 divided by 8.1 equals 33.1. 33.1 atmospheres of pressure. That's the pressure inside that container under those conditions when you're making the alcohol. And that's how we use it. We use our stoichiometry just like we did before. We just found the number of moles. Once we found the number of moles, you know what conditions it's in. We can use P equals nRT to find the pressure. Now, if you knew the pressure, you can find the volume. If you knew the pressure and the volume, you can find the temperature. If you knew the pressure, volume, and temperature, you can find the number of moles. As long as you're solving for one variable, you can use those equations in software. Okay? That is basically the end of the chapter. Any questions on chapter 10?
No.
No?
Yes, there's a question that's driving me nuts.
Okay, what's that?
It says, so I went from millimeters of mercury to atmospheric ATM. And then from, okay, so the last, I can't get the last part. It's asking me to convert 1,125.3 millimeters of mercury to PA.
Pascals, okay? You want to go to that and you want to go to PA, right?
Yes.
Pascal units used in Canada and some European countries and measuring from parameters.
So what I'm doing is I'm going, so I put the, oh, I think I see what
Okay, let me just find the conversions for it. Okay. So we have one atmosphere equals 101.3 kilopascal. So we're starting with 1,125.3 millimeters of mercury, right?
yes.
Okay. Now,
And
one
then
millimeter of mercury is the same thing as an atmosphere.
7
Okay. So our atmosphere, one atmosphere.
is 760.
Yeah. No.
Oh, am I doing it?
Convert to atmosphere. So yeah. So 760
Yeah,
millimeters of mercury is equal to one atmosphere.
yes.
Okay. One atmosphere is equal to 101.3 kilopascals. So one atmosphere is equal to 101.3 kilo.
I'm doing it right. I'm just not inputting the number.
Right?
Yeah. So I get from that.
We're not done yet.
Oh, we're going further. That's what I,
because it wants to go to pascals, right?
yes.
10 to the third pascals. So you went from millimeters of mercury in atmospheres to kilopascals to pascals. Remember, kilo is 1,000 in a metric system.
Yes.
Okay, so it wants to go to pascals, not kilopascals. So there's your numbers.
And
Okay, so you put in 1125.3. Okay, divided by 760 times 101.3 equals, and equals, so that's equal to 149.990645 times 10 to the 3. So we're going to move this over 1, 2, 3 places. So it's going to be 1 point, how many, we got 1, 2, 3, 4, 5 single digits. 1.49995,
90.
right? 1, 2, 3, 4, 5 times 10 to the, and I move this So the point was here, so I moved it 1, 2, 3, 4, made it smaller by 5, make this bigger by 5. 10 to the 5 pascals.
It's the steps of conversion that gets me, like how many times I have to go from one to the other.
Right, you got to get it to what the unit that you want.
Yes.
So millimeters of mercury went to atmospheres, atmosphere went to kilopascals, kilopascals went to pascals. You just got to keep going until you get the unit that you want at the end, which is pascals in this case. That make sense?
Yeah. Thank you.
Oh, no problem at all. Any other questions on chapter 10? Okay, we have some questions that were emailed to me or texted me on the phone. So let's go over those. And then we'll go on to there's some without their email too. So let's do the phone ones first. Let me find my text messages here. All right. There are a couple here. Let's pull up the first one. And it says, gives you the formula calcium iodide and silver nitrate. Okay. Okay, this is a stoichiometry one. And it gives you the formula. Let's do this. So let's do the formula calcium iodide plus AgNO3, silver nitrate goes to silver iodide plus calcium nitrate. Okay, and you have to balance the equation. Put a 2 here and then 2 here, and that should balance, right? 1 calcium, 2 iodine, 2 iodine, 2 silver, 2 silver, 2 NO3, 2 NO3. Perfect. And it says how many moles of silver iodide will be produced. So how many moles of silver iodide? So question mark moles, okay, of silver iodide will produce 158 grams of calcium iodide. Like it says, write everything down so you can see it without looking back at the question. And we're good. So it says there's your formula, there's your equation. Okay. And you want to know, if I start with 150 grams of calcium iodide, how many moles of silver iodide did it produce? And this is just like we were talking about the Deanna. Where do you stop? So you know what you're starting with, right? We always know what we're starting with. We're starting with 158 grams. You know, this is just like the conversion we were doing. Exactly. So 158 grams of calcium iodide. And I want to convert that into what? So I can use my chemical equation. I want to convert that into, chemical equations are always in moles. So we want for moles of calcium iodide. So calcium weighs, what does calcium weigh? Calcium weighs 40.1 basically. So 40.1. And iodine weighs, like I said, just rounding numbers off here, but go back. 126, 127, 127 times 2. Like I said, you might have to go back and read these, I'm just rounding these off. So 127 times 2 equals 254 plus 40 gives you 294. So 294 roughly grams per mole. And then you know your equation goes from moles to moles. So we have moles of calcium iodide, that's what we calculated. And I want to go to moles of, what am I looking for? Moles of silver iodide. Okay, what's your relationship? Calcium iodide has 1 mole. Silver iodine has 2. And that's where we stop. We don't keep going because we want moles of calcium iodide, and we have right here moles of silver iodide. Okay. All right. So we take 158. Oops. We'll calculate back again. 158 divided by 294 times 2 equals 1.07 moles of silver iodide. Okay. The key is to knowing when to stop your conversions, when you reach the point where you're looking for their specific answer. And that's what they're looking for, roughly 1.07 moles of silver iodide. That make sense?
Yes.
All right, perfect. Let's pull the next one. Where did it go? That was the first one. 1, 2, second one. Okay. How many grams of calcium chloride produce 30 grams of carbon? All right, next one is a similar problem, but it's a limited reagent one. So it says, it gives you a formula, calcium carbonate plus hydrochloric acid goes to calcium chloride plus water plus CO2 gas. Okay. And it wants to know how many grams of calcium chloride will be produced. How many grams of calcium chloride? Oh, I hit the wrong button. How many
Steve?
grams of calcium
Steve,
chloride?
someone's calling.
It's okay. Don't worry about it. Just leave it alone. Put it back where it was. Okay. How many grams of calcium chloride will be produced? Okay, so you want to know how many grams. Again, write it so it's all in front of you. When 30 grams of calcium carbonate, 30 grams of calcium carbonate is combined with 13 grams of hydrochloric acid. Okay. Perfect. So we're mixing two things together. We got to find out which one runs out first. Just like we're making our sandwiches, right? Okay, we have a limiting reagent here. So let's figure it out. Everything's first step is what? Balance the equation. One calcium, CO3 broke up. So one hydrogen, two hydrogens. We're gonna put a 2 here to balance our hydrogens. And so one calcium, one carbon, three oxygens, two hydrogens, two chlorines. Is that balanced? That was it? That was easy. Okay, it's balanced. All right, so now we convert everything into moles because we have to go to moles to use the chemical equation. So we have 30 grams. Well, let's start with calcium carbonate. Calcium carbonate, we have 30 grams. How many grams per mole? We have one calcium, which is, calcium is roughly 40. Let's put it up here out of the way. 40 plus carbon, which is 12. That's a 0. Plus oxygen, 16, 32, 42, 48. Okay, we end up with 10, 5, 6, 100. 100 grams per mole, roughly. Okay, so 30 divided by 100 comes out to 0.3. 0.30 moles calcium carbonate. Hydrochloric acid, we have 13 grams of hydrochloric acid, and chlorine is 35.5, so 36.5, because hydrogen's 1, chlorine's 34.5, 35.5, 35.5, so 36.5 grams per mole. So that comes out to, what is 13 divided by 36.5? So 13 divided by 36.5, hit the wrong numbers, equals 0.356 moles. So which one of those is going to run out quicker? Let's just pick one. Let's pick calcium carbonate. So calcium carbonate, we say the X, and then HCl is 0.356 equals calcium carbonate is 1 and HCl is 2. That's what we set up, right? Those are ratios. We're just picking this one as our unknown because you got to pick one. It works the same no matter which one we pick. Okay, so I put an X for calcium carbonate for number of moles, and then I know moles of HCl is 0.356. Okay. Okay, and it's in a 1. Calcium carbonate is 1. HCl is 2 relationship. So X equals 0.356. We cross multiply. 2X equals 0.356. X equals 0.356 divided by 2. 0.178. Okay. Do I have 0.178 moles of calcium carbonate? Yeah, I got 0.3 moles of it. So I got extra. So if I have extra calcium carbonate, this is my limiting reagent right here. Everybody see why? Because I need 0.178 moles of my calcium carbonate. I have 0.3. So I got extra calcium carbonate. So if I got extra calcium carbonate, I don't have enough HCl. That's going to run out at first. Okay, so that's what I'm going to use to our calculations. So I've got 0.356 moles of HCl. Okay. And we're going to have moles of HCl, 2 moles of what I'm looking for, which is calcium chloride. I got 1 mole calcium chloride, 2 moles of HCl. And then moles of calcium chloride, 2 grams of calcium chloride. Calcium chloride, calcium is 40. Chlorine is 35.5. I keep drawing a blank. I don't know why I keep doing that. 35.5, so 30, so 70, 71, right? Yeah, 71. 71 grams per 71 grams of chlorine comes out to 111 grams of calcium chloride. So we take 0.365, 0.365, about 356, sorry, 0.356 divided by 2 times 111 equals roughly 19.8, right? Grams. Calcium chloride. So that's the limiting reagent one, and you will have one of those on your final, just so you know. Okay. Whenever you have 2 reactants, you got to figure out which one's going to run out first. And then you use that one for your calculations, because once that one runs out, the reaction stops. That's all you can produce. And you just do one with that one as your unit to start with. Does that make sense? I think there's another question. So it said, oh, which reactant is in excess? What's in excess is calcium carbonate. That's going to be in excess. Okay. Hey, is that one good? That's a good question. Know how to do one of those. It's like
It also asked how many grams of the excess reactant will remain after the reaction is complete.
oh, how many's going to remain? So how much are you going to use up? So we're going to use, where am I on? This is how the easiest way to do this to calculate that. We're going to go with, we're going to use up 0.356 moles of HCl. So 0.356 moles. Did I ask in grams or moles? Is left over.
It said grams.
Okay, 0.356 moles of our HCl. So we have moles of HCl, 2 moles of calcium carbonate. Okay, and it is a 1-to-2 relationship. So that's how many moles we're going to use. Okay, so 0.356. Let's get my calculator out here. 0.356 divided by 2 comes out to 0.178 moles of calcium carbonate. That's how much we're going to use. Okay, so we've got 0.3. So 0.3 minus 0.178 is going to give you how much you have left over. So we have 0.3 minus 0.178 is going to equal 0.122 moles left over. And you want to convert that into grams? How many grams per mole? Put a zero for that so we see it. Okay, so calcium carbonate was 100 grams per mole. We calculated that already right here. So 0.122 times 100 is 12.2 grams of calcium carbonate is going to be left over. Did that make sense?
Yeah.
Okay, perfect. I think there were 2 more questions on that, right? Okay. And the other one, what is the actual yield of iron in moles? Theoretical yield, percent yield. Okay. All right, let's do another equation here with theoretical and percent yields, which is really good. So iron 3 oxide, which is Fe2O3, plus carbon goes to Fe, iron, plus carbon monoxide. And they balance it for you. In this one, there was 3 carbons and 2 and 3. I just always double check. 2 irons, 2 irons, 3 oxygens, 3 oxygens, 3 carbons, 3 carbons. We're good. Okay, it says combining 0.226 moles of the iron oxide with excess carbon, so we've got abundant extra carbon floating around, produces 16 grams of iron in the laboratory. Okay. And it says, what is the actual yield of iron in moles? Okay, the actual yield is 16 grams. That's what we did when we did the experiment. You got 16 grams. So you got to convert 16 grams into moles. 16.0 grams of carbon, grams of carbon dioxide. This is grams produced. Oh, no. Whoa, I did that backwards. I'm sorry, I put the numbers in the wrong place. Okay, produce iron, 16 grams of iron. 16.0 grams of iron was produced. And it says, what is the actual yield of iron in molecules? So the actual yield is 16 grams. And how many grams per mole? Because it asks how many moles it is. So iron weighs 55.8, so 56, we'll round it up, 56 grams per mole. So roughly 16 divided by 56. Come on. So I want 16, get the numbers right, divided by 56 equals 0.286. Okay. So 0.286 moles of iron is your actual yield. Okay, that's the first part of the question. Second part of the question. Well, let's go back up here. Okay, that's actually, what is the theoretical yield of iron in moles? The theoretical yield is what we calculate. So if we have 0.226 moles, okay, of Fe2O3, and we want to know how many moles of iron we will produce. So we have 1 mole Fe2O3 to 2 moles of iron. So your theoretical yield is going to be 0.452 moles of iron. That's your theoretical yield. That's what we calculated. Our actual yield is what we got. This is actual, and this is theoretical. Those are in moles. So far, so good?
Yeah.
That's what we could produce if everything goes right. That's what we actually produced in the lab. So that's in moles. So it wants to know the next part. There's 3 steps to this one. What is the percent yield? So the percent yield is your actual yield divided by your theoretical times 100. So 0.286 divided by 0.452 times 100.
The steps are what kills me. It's
What's
the
that?
steps. It's the steps is what kills me from going from A to Z.
Right. Just take your time and think it through.
Yeah.
Can
Can you not time our final?
No, I can't do that. But it's the more you do it, the better. I mean, you need to practice because I make it look easy. But what you got to do is go through and just.
Yeah, you make it look really easy.
So 0.286 divided by 0.452 times 100 equals 63%. And that's your percent yield. What you actually produce divided by what you should have produced, only went 100%, times 100 give you a percentage. Does that make sense?
Yes.
Okay. And there's one more question, I think. Oops, here it is. Okay, chlorine gas can be prepared in a laboratory. By the reaction of hydrochloric acid and magnesium fluoroxide. All right. A sample of 41 grams of magnesium oxide is added to a solution containing 40 of HCl. What's the limiting reagent? What's the theoretical yield? Okay. So another limiting reagent. Alton, what's up?
That's it.
All right, so let's do that. So we have 4HCl plus magnesium oxide, manganese oxide, goes to MnCl2 plus water plus chlorine gas. Okay, I think they balance it for us. And 42.9 grams. .9 grams. It's added to a solution containing 43.1 grams of hydrochloric acid. And it wants to know what's the limiting reagent, which one's going to run it first. And it also wants to know the theoretical yield. Theoretical yield of Cl2 of chlorine. It wants to know how much, I assume it's in grams. It doesn't say. Theoretical yield, does it say grams on this? Yeah, it says grams, CO2. Okay. In grams. Okay, so which one's limiting reagent? Okay, convert them both into moles. So 43.1 grams, and this is HCl. And then we have grams per mole. And high chlorine is 35.5, hydrogen is 1, so 36.5. Okay, so 43.1. Where are we at? 43.1 divided by 36.5 equals 1.18 moles of HCl. We want to use manganese 4 oxide, MnO2. Okay, and I have 42.9 grams. How many grams per mole? Okay, manganese is, don't touch those. What's those? Put that back. Okay, manganese is 54, so manganese is 55. So we got 55. And oxygen is 32, 16 twice. So 87 grams per mole. That's what MnO manganese 4 oxide is. So 42.9 divided by 87 equals 0.493. All right, let's pick one and do the comparison. So let's set hydrochloric acid equal to X. And then 0.493 is equal to hydrochloric acid is 4 from our equation, and manganese is 1. So X equals 4 times, cross multiply. X equals 4 times 0.493. Which is 1.97. I'll come back here. Keep hitting that, 1.97. So do I have 1.97 moles of hydrochloric acid? No, I've only got 1.18. So I'm going to run this one first. It's not going to have enough. I don't have enough to match that, to match 1.97. So HCl is my limiting reagent. And it says that makes sense. That's the first question.
Yeah, that makes sense.
Okay, so there's my limiting reagent. So now we use that to calculate a theoretical yield of chlorine gas. So we have 1.18 moles of HCl. That's what we're starting with there. That's my limiting reagent. And I have moles of HCl. And I want to go to moles of Cl2 gas. Does it wants it in grams, right? Yeah, it was grams. I remember looking at that. So moles of CO2 is 1. Moles of HCl is 4. And then I want grams per mole of chlorine, which is CO2, 35.5 doubled is 71. So we'll do the math at 1.18 divided by 4 times 71 is how to get a negative. I hit something wrong. Hold on. Can't get a negative number. 1.18, right? 1.18 divided by 4 times 71 comes out to 20.9 grams of CO2. Roughly, that's roughly your theoretical yield of CO2. Does that make sense?
Yeah, it does.
Yeah, I think there was one more part. That's your theoretical yield. It says if the yield of the reaction is 77.1%, what is the actual yield of chlorine? Okay. So I know it gets you the actual yield is 77.1%. So your actual yield divided by your theoretical, this is your theoretical yield. This is your actual yield divided by 20.9 times 100 is equal to your percent yield. The percent yield of 77.1%. Okay, so here's your percent yield was 77.1 they gave you, and your percent yield is your actual yield divided by your theoretical yield times 100. So your actual yield we don't know, but we know your theoretical yield times 100. So let's solve for A. A is equal to 77.1. Let's do this on the calculator so we get everything right. 77.1, and then we're going to divide 100 by both sides. So that's 0.771, and then times 20.9 to both sides. So your actual yield is 16.1 grams. Just solving for A, your actual yield. Divide by 100 times 20.9 to get A by itself. Does that make sense?
Yeah, thank you.
Yeah, that was a good question. That was a real good question.
Yeah, those really, like the yields and all the theoreticals and all that stuff, it's just like too much for me sometimes.
So it just makes you just take your time and put it where they really belong. So I know you guys can do the math. It's just a question of thinking it through and understanding where to put things. You're right. But good.
Exactly.
Exactly.
That's what gets us, like what goes where and when.
Yep. All right. And I also had questions on the platform. Let's see, where am I at? And I think I lost my, hold on. There we go. We're back on that. Raise that back up. All right, let me go to my email. Okay. And a researcher studied the nutritional value of a new candy, places 3.6 gram sample inside a bomb calorimeter, combusted in excess oxygen, so it blows it up. Observed temperature is 2.7 degrees centigrade change. The heat capacity of the calorimeter is 33.8 kilojoules per Kelvin. Should be the same in Kelvin or centigrade, so that better. How many nutritional calories are there per gram of the nutritional calories? Now, a nutritional calorie is 1,000 calories. That's going to be a big C and a little c, just by definition. So let's, and we know the heat capacity. Q, let's go back here. Q, our heat is equal to heat capacity times the change in 100. Okay. So we know the heat capacity, we know the heat capacity, we know the change in temperature. So we know the Q value, how much heat was given off. Okay, so Q is equal to our heat capacity, which is 33.8 kilojoules per Kelvin. And the change in temperature is going to be 2.73 degrees centigrade. And degrees centigrade is going to be the same change in temperature, whether it's Kelvin or centigrade, because you're adding 273 to it both times. So it won't make any difference. So 2.73 times that. So you end up with the heat value is going to be in kilojoules. And you want to convert that into kilocalories. So 33.8 times 2.73 comes out to 92.27 kilojoules. And the conversion for kilojoules to calories is what? I have it to joules to calories. Let me look that up real quick. I don't have those conversions memorized. Let's see, convert kilojoules to calories. So 1 kilojoule, looking this up, 1 kilojoule is the same thing as 0.239006 kilocalories. Okay. So 1 kilojoule is equal to 0.239006 kilocalories. And a kilocalorie is equal to a calorie. So 1 kilocalorie is equal to a calorie with a capital C. That's our nutritional calorie. Because if you look at a Snicker bar and it says 7 calories, you're going to buy it. If it says 7,000 calories, you're not going to buy it, right? So it's all just a matter of looking at things. Okay, so 92, let's do the math, 92.27 times 0.239006 equals 35.99 nutritional calories. Okay, but that's not your answer. That's not what the question asks. So that's how much that's how much nutritional calories are produced for 3.6 grams of the candy. It asks how many nutritional calories are there per 1 gram of the candy. So you've got 35.99 calories with a capital C per 3.6 grams. So how much is it per 1 gram? This is how much is calories per gram. So it's 35.99 divided by 3.60 equals 9.99. That makes that 10. It's roughly going to be 10. 10.0 nutritional calories per gram of the candy. Does that make sense?
Yeah.
Okay. So it's 2 steps. You got to convert. You got to use your specific heat in the bomb calorimeter to calculate how many calories. And you got to realize 1 nutritional calorie is a kilocalorie. It's 1,000 calories. So once you've calculated that, then you got that much per 3.6 grams of candy. And that's how much each gram of the candy is. So this is calories, nutritional calories per gram. Okay, so it comes out to 10 calories, roughly. Okay. Next one. Classify each statement of recommendation as true or false. I can't see the bottom line. I can see it coming from here. Let me see if I can pull that up.
There's 2 pictures for that
Yeah, I
one.
got it. Okay. Okay, so I got 6 statements, dude. What are you going to put as true or false?
What's this?
All right, so these are true statements. These are false statements. First one, radio waves have longer wavelengths than visible light. Yeah, but I mean, it's simply look it up. Look at the spectrum. Look at, let's do wavelengths of, I'd have to look up in the book, but we can do it this way. Radio waves. Radio wave LNG length range. So your radio wavelength range from, so from 1 millimeter to 300 meters. So 1 millimeter. Okay, radio waves have the longest wavelengths in the electronic spectrum, 1 millimeter to several hundred, so 300 meters. And what is the wavelength of visible light? Visible light was like 600, 700 nanometers. Radio wavelength, visible light. I said you look those up in the book. I don't expect you to memorize. Visible light is about 380 to 7, so about 500 nanometers. So visible light is about 500 nanometers, between 360 to 780 nanometers, which is 10 minus 9 meters. Radio wavelengths are 1 meter long, up to 300 meters long. Okay, so radio would have the largest one. So radio waves have longer wavelengths than visible light. That one's true. So radio waves. Okay, that one's true. X-rays have a lower frequency than visible light. X-rays have a lot more energy than visible lights. That's false. Okay, X-rays have extremely high frequency. Remember, frequency is cycles per second. So your frequency is, coming like that, much more energy than visible light. Okay, so that one is false. This is X-rays. Okay, the light from the sun includes multiple types of electromagnetic radiation. I would say that does. Let me double check. Sun and types of electromagnetic radiation. Radiation. Okay. Yeah, it gets a solar spectrum. So solar rays includes visible light, ultraviolet light, infrared, radio waves, X-rays, and gamma rays. All that's included from the sun. So the sun gives you a bunch of different types of electromagnetic radiation. So that's true. Light from the sun includes multiple types of electromagnetic radiation. That's where you get sunburns, things like that from the UV light. So this is light from the sun. That one's true. And ultraviolet radiation is lower in energy than infrared radiation. I think it's higher. Okay. Ultraviolet. Radiation, let's see, ultraviolet radiation. What about infrared? Okay, ultraviolet. Yeah, ultraviolet carries more radiation because it does more damage to your skin. Okay. Infrared radiation is less radiation.
Where's Mommy and Susie?
Both of you. All right, so ultraviolet radiation is going to carry more energy than the infrared radiation. So that one is, what does it say? Ultraviolet radiation is lower in energy. Hey, hold on a second. Ultraviolet and out of here now. One. All right, so we've got ultraviolet radiation is lower in energy than infrared. No, it's higher. That one's false. So UV radiation. That's UV radiation. Because UV radiation causes skin damage and stuff like that. Infrared radiation does not. So it'd be higher in energy. Okay, if the frequency of a wave increases by some factor, the wavelength of that wave decreases by the same factor. Number C is equal to wavelength times the frequency. So if the frequency of the wave increases by 2, the wavelength will decrease by 2 because C is constant. This can't change. So if this increases by 2, this has to decrease by 2 to stay the same. So that one is true. So this one is true. This is frequency and wavelength. Okay. Speed of electromagnetic radiation varies with frequency. The speed of electromagnetic radiation. I don't know what you mean by speed. They all travel the speed of light. The speed of electromagnetic radiation. Let me check and see that's in the book. What do they have for that? It's not a great question. Electromagnetic radiation. Let's see what they're asking Yeah, so all the radiation, they all travel at the speed of light, just different frequency, different wavelengths. They're all gonna be constant to the speed of light, so does the speed, the frequency and the wavelength varies, but when you multiply them, they're always gonna equal the speed of light. So I'd say that one's false. I don't think it's a good question, but I would put that one as false. Does that make sense?
Yes, thank you.
Yeah, that last one's not a real good question. The other ones are all pretty good. That last one, because you don't measure speed with electromagnetic radiation. You measure frequency and wavelength, and you get a speed. So I'd say that one's false because I don't really understand what they're trying to say, but okay. So far, so good?
Yes, thank you.
All right, and then I think there's more. It says the temperature of an object increases 70.9 degrees centigrade when it absorbs 381 joules of heat. Calculate the heat capacity of the object. Okay, so we did one similar to that, and that was same formula that Q is equal to the heat capacity times the change in temperature. Okay, so the temperature of an object increases by that when it absorbs. Okay, so the heat capacity is equal to Q divided by delta T. Just rearrange that. So Q is equal to 3821 joules. And the change in temperature is 70.9 degrees centigrade. So 3821 joules, 3821 divided by 70.9 equals 53.89 joules degree centigrade, per degree centigrade. Okay. So this should be the heat capacity of the object. Okay, now it says the second part says the mass is 34.1. Use the Hunter composition of the object. Specific heat. Specific heat is joules per gram degree centigrade.
I got the second part.
Oh, you already got that?
Yeah, I got the second part.
Okay. Yeah, they just substitute that number back in. And the last one is perform the calculations. It says 6.5 minus 6.06 divided by 4.76, right? So do us in parentheses first. So let's take 6.5 minus 6.06, and that's equal to 0.44. Now, this can be a significant figure one. It all depends how you do it. This is good to 2 places past the decimal. That's only good to 1 place. But I would say leave it at that, divided by 4.76, and you're good to 2 significant digits. So 0.44 divided by 4.76. 0.44 divided by 4.76 comes out to 0.092436. So I would say 0.092. Sometimes I might put 0.0924 depending on where they rounded it up, depending on how they had it. Or actually 1 significant digit. Okay, if they round it, it depends where they rounded it. Okay, because actually 6.5 is going to be 0.4 because you're only good to 1 place past the decimal. So 0.4 divided by 4.76. So it would either be this answer or depending how they did it with the book, would be 0.4 divided by 4.76 and 0.08. How you round it up. I think it would more closer to this answer with the book.